today I am going to talk about another type of a smart material which is known as magnetostrictive smart material. So, in the earlier material that I have discussed with you, that is the piezoelectric material, electric field and mechanical field were coupled in that particular system, which means by using electric field we have generated mechanical deformation, and similarly by using mechanical force we have generated electric voltage. For the magnetostrictive material, this electric field is to be now replaced by magnetic field. That means by using magnetic field, we will generate mechanical deformation and the other one, that is mechanical deformation or force, say mechanical force, will create a change in magnetization. Unlike the charge generation, here it is change in magnetization. So, this is the first one is our direct effect, just like very similar to the piezoelectric material. This is our direct effect and this is our reverse effect. Okay. So, this is what we are going to study in today's lecture. Now, magnetic force is something which was in the deep history, it was always considered to be a very mystic kind of a force, because this is one force you see which you cannot actually visualize it or visually determine that the force is there, but the force can be very considerable. So, this is what is considered to be a magical power of the magnet, and that awed people of early civilizations as if it is a strange force which comes from the rocks. Basically, these magnetites are available in the rocks. If you go through the stories of Arabian Nights, you will see that Sindbad's story of that rocks attracting ships. It's also a very similar version. So, the rocks that attract shoes and swords without revealing itself. So, people considered it as a magical power. Now, that is about the magical power of the magnet. But James Prescott Joule in 1842 noted another interesting thing of the magnets, and that is, if you take a ferromagnetic material and if you apply the magnetic field on it, it actually changes its size or length. That change in length is very small in iron, but nevertheless it changes its length, and this was discovered in 1842 by James Prescott Joule. I would rather tell you that is the beginning point of the magnetostriction. So, what I am going to talk about today is that what is magnetostriction, and there are some examples and which will help us to understand the phenomena, a brief history of magnetostrictive materials and what are the different effects of magnetostriction, so that we develop a bit of a background about it. Now, what is the magnetostriction? Magnetostriction in a material is something which refers to the change in the size of the system due to domain migration and reorientation under applied magnetic field. For example, you consider the first case where a magnetic material, as you know, is always having dipoles, magnetic dipoles in it, and each dipole has its own direction, but these directions are very randomly aligned. So, that means in terms of north south, suppose they are very randomly aligned, and that is as there is no applied magnetic field. The moment you apply the magnetic field, they will all get properly aligned, and that would create an expansion in the system. As a result, you are going to observe the magnetostriction in the system. So, this kind of mechanical deformation which happens due to domain migration and reorientation in a this type of a material under applied magnetic field H, that is what is actually magnetostriction. There are two terms here. which is important. One is called magnetostriction, another is called giant magnetostriction. While magnetostriction is true for all the materials, but a subset of that shows very large magnetostriction, and that is generally referred in the literature as giant magnetostriction. Now, if a crystal of ferromagnetic material is initially at a compressed state, it is found that this effect is actually more pronounced. In fact, there is another reason in which this effect can be utilized if it is in a compressed state, or if you use a biased magnetic field, you can actually generate both expansion and contraction. Otherwise, magnetostrictive effect basically creates expansion in the system. All ferromagnetic elements show magnetostriction to different degrees, but all of them shows magnetostriction. And it is observed that out of the general ferromagnetic materials, it is cobalt which shows the maximum magnetostriction, which is about 50 micron strain, where it actually saturates. Now, you may see that there are some materials which shows actually negative magnetostriction. So, what it means is that if positive magnetostriction means expansion, then negative magnetostriction is some of the rarer cases where it would mean that by using magnetic field you can even contract the system. However, all these 14, minus 33, 50 in absolute scale, these are all very low. Even permalloy, which is 27, is very low. But it is with the discovery of the later phases of magnetostrictive materials like dysprosium and iron alloy, or terbium iron alloy, or terbium dysprosium and iron alloy, you will see that in these cases magnetostriction is quite high. And the other interesting thing is that very similar to piezoelectric material which has a Curie temperature, what it means is that beyond that temperature that piezoelectric property gets lost. Very similar to that, magnetostrictive materials also has a Curie temperature beyond which the magnetostrictive property gets lost, and that Curie temperature actually is varying for different materials, but on an average for these giant magnetostrictive materials, these are actually 600 plus in terms of Kelvin. That means it is about 300 degree or so. So, what it essentially means, up to 200 degree or 250 degree, this system would work very well. Now, we talk about a brief timeline of the magnetostrictive materials. As I told you that James Prescott Joule first discovered magnetostriction in nickel, and that was what was Joule's discovery, that is in 1842. 1865, the reverse effect that came into the notice of Villari. So, he found out the inverse of the Joule effect, and 1926 people were able to see this anisotropy in single crystal iron due to the development of material science. And 1965, for the first time, beyond the general ferromagnetic materials, people found magnetostriction in rare earth metals like terbium and dysprosium. This was initially found out by Clark and then other people in the Naval Ordnance Laboratory. It was later on, 1972, it was found out that instead of using pure terbium or dysprosium, if you use terbium iron compound or dysprosium iron compound, you can actually get magnetostriction at up to a much higher degree of temperature. And then on this terbium iron compound, if you add a little more dysprosium, you are going to get a much larger magnetostrictive effect, and terphenol D, which was actually discovered by Clark. And later on, people found out that if you use polymer matrix and the particulate composite of terphenol D, you can make a nice composite out of it, and you can give nice shapes to the system. Later on, there was another material. Instead of terbium, it was found that if you use gallium and then iron and then galphenol is the new material, that is actually more rugged magnetostrictive material. It was developed in NSWC by Clark, and that was found to be a much more rugged magnetostrictive material. Also, people have worked on oriented particulate composite, where these magnetostrictive materials are properly oriented to get maximum kind of displacement or maximum shape change out of it. So, the one which is mostly used is Phenology, and as you can see that the name itself tells us what is the composition of it, because there is this Fe, which is the iron, then TER is the terbium part, so it is terbium iron compound to begin with, and this NOL is nothing but Naval Ordnance Laboratory of USA, who claimed the first people to discover it, and D is the dysprosium. So that's how the terphenol D name actually appears. It looks very shiny, and in fact it is very explosive. So a small video in which you can see that if you hit this magnetostrictive material with a hammer, it is releasing huge amount of energy. So that's basically the energy density is very high in these magnetostrictive materials. Now, where are we in terms of the performance comparison between magnetostrictive material and shape memory alloys, etc. Now, PZT, the actuation mechanism is piezoelectric actuation. For terphenol D, it is a magnetostrictive material, so it is magnetostrictive actuation, and for SMA, it's a thermal driven process generally. So the elongation, if you compare, you would see that terphenol D gives a medium performance, not so high as SMA, not so low as the piezoelectric material. In terms of the energy density that it shows is somewhere around 20 joule per meter cube, which is quite high. And in terms of the bandwidth, once again it is in the middle, like 100 kilohertz by piezoelectric material, or shape memory alloy as 0.5 kilohertz. This fellow shows about 10 kilohertz, and the hysteresis is about 2% in the whole thing. So it means it behaves in a very linear manner, and the cost wise also it is actually double the cost of terphenol D, but it is easier to actually fabricate them. So in terms of that, it is easier sometimes than the PZT or other counterparts. So this is a relative comparison between these materials. Now I told you that magnetostrictive material shows something like 2000 parts per million or little more than that in terms of the strain, the active strain. So how much does it mean in terms of the change in length? So let's say I choose 100 millimeter of a beam and I apply these material over it, and then if the free strain is something like 2000 parts per million, and if you join it, you are going to see that it is slightly lower than 0.2, but between 0.16 and 0.2, that's the change in the absolute length that you can expect in such situations from this material. So this gives us an approximate idea of the type of change that you are going to see in this material. Another interesting thing is that the terphenol D has a butterfly curve, okay, because you can see that the shape here is like a butterfly. Now in this butterfly curve, what we are trying to show is that if you change the magnetic field, you are going to see that there is a reversal, but that reversal is not in terms of sign change. So you can see that with respect to positive voltage, you get some shape. With respect to the negative voltage, you get the reverse shape in the magnetostrictive material. However, the point that is interesting is that in all the cases, you are only getting positive strain, only expansion. So how can we generate a kind of a tension compression sequence so that vibration gets generated in the system? Because it is a butterfly curve, it does not go to the other side. To do that, what we use is a bias current, and also we actually operate it across that bias current. Suppose somewhere this is what is my bias magnetization, and then we keep that fixed, and then we actually take a bandwidth on which, as we change this bias, it is going to show relatively either less strain or more strain. Thus you can generate your own magnetostrictive transducer. So that's the advantage of this system. Now, what are the attractions of this magnetostrictive material? Surely so many people are working on it, there must be something which attracts them. One, I already said, that the large force generation. The other interesting point is that its signals does not decay with time. So it actually, much unlike the piezoelectric materials where the discharge happens very fast, it does not get discharged, so to say, very fast. So if you consider a magnetostrictive transducer to apply, it will be cost effective in the low frequency band and could be effectively used for deep sea measurements due to the superior mechanical techniques. There is one such transducer, Talon, that is Tactical Acoustic Littoral Ocean Network Talon software sonar system, that uses magnetostrictive terminal D for underwater submarine detection, like Atrima products. If you see, you will see this type of applications into it. Magnetostrictives are actually, transducers are very active in terms of sensing very small displacement and converting them to a very good significant amount of change of magnetization or change of voltage. So that is the that is why as transducer these things are used in various subsea applications. Now, magnetostriction in a solid rod, how would it happen? So if I consider a solid rod and if there is a solenoid wound around it, and in that solenoid let us say I am applying a current I, which is going to generate a magnetic field H on the core that you can see here. Let that core be magnetostrictive core. Then due to the application of this current, the magnetic field will create an expansion, initiate, and it will become from L to L plus delta L. And if you plot these delta L over the length, what you are going to see, and that if you actually plot with respect to the change in magnetization, you are going to see that famous butterfly curve, which says that even if we actually change the magnetic field from positive to negative side, still we are always getting expansion in the system. Now, if I vary the magnetic field in this type of a system, suppose initially there is no magnetic field. So you can see the domains here which are very arbitrarily aligned. Now, the moment we apply the magnetic field, what will happen is that there are some axes which are known as easy axes. So if my magnetization favors the easy axis, then the grains will be growing along the easy axis as it has grown in these cases. And then even further, if you increase this electric field intensity, the magnetic field intensity, what you will see is that all the magnetic dipoles got very nicely aligned. And this, if you increase further the intensity of the magnetic field, you can almost make all the magnetic field dipoles to be parallel to the system. So starting from the basic demagnetized state, thus for a terminal D material, you can get a reasonably good change in shape by following these steps. Now, just like piezoelectric, we have two effects, like one is direct effect, another is reverse effect. Something very similar is there also for the magnetostrictive materials. For example, if you look at the reverse effect that it creates, there is this Joule effect that Joule has discovered, okay, that the magnetization is changing the length. Then there is this Weidmann effect, in which he showed that if this magnetic field is helical in nature, then it will not create length, rather it will create torque. And then the magnetovolume effect, in which if you change the magnetic field, you are going to see a good change in the magnetic volume of the system. Now, all these change of volume, if you say, or change in dimensions, etc., all these can be used in terms of developing actuators for the system. But what are we going to do for developing sensors for the system? Then there are three techniques that you can use. One is called a Villari technique, Mathieu effect, and the Nagoka-Honda effect. The Villari effect, actually what it does is that if there is a strange change, then there will be a change in magnetization in the system. The Mathieu effect is very strange. If you actually apply torque, then you are going to see the helical anisotropy and EMF induction in the system. So that is what is our Mathieu effect. And the Nagoka-Honda effect, in this actually, if there is a change in the volume in the system, then there will be a change in the magnetic field of the system. So that is Nagoka-Honda effect. But mostly what we use are the Joule effect, Weidmann, magnetovolume effect, and the Villari effect of the system. Now, if you look at the constitutive equation of magnetostrictive material, then there is two important one. One is from the direct effect point of view, and that means where you are using the mechanical force field and you are getting the change in terms of the electrical or magnetic field change. So which is what you can use in terms of the mechanical force field change. For example, Villari effect you can use in terms of developing the sensor here, and the other one is where there is a application of the magnetic field and you are getting a change in terms of the mechanical strain, which is what is used in terms of the actuator equation. Now, if you look at each one of these equations, in the Joule effect, you can see that the strain, mechanical strain, can be either related to the mechanical stress, which is the normal Hookean part. Also, you can use the magnetic field intensity along with D. D is nothing but the magnetostrictive constant. You can use that in order to generate the mechanical strain in the system. Similarly, if you look at the Villari effect, which is more used for sensor development, here if there is a change of magnetic field intensity, then there will be a change in the magnetic field displacement, which is fine. But in addition, if there is a change in stress, or that means if there is a change in strain also, then also there will be the change in the magnetic flux density B, and that can be captured in terms of change of voltage through a pickup coil, etc. So that is what is the constitutive equation, which looks linear, but it is actually linear in a very small range, and this is used in terms of developing actuators and sensors. What are the major applications? We can use this material for active vibration and noise control system, for machine tools, for servo valves, hybrid motors, for sonar devices and tomography, automotive brake system, micro positioning, and ultrasonic cleaning, for machining and welding. So there are varied applications in which actually you can use it. The initial application was in terms of sonar devices, but now you see there are so many different applications of these magnetostrictive material. In terms of vibration sensing, there are two approaches. One is to develop particulate composite, like Phenology particles are milled, of micron to submicron size and are dispersed in a suitable resin and cured to form sensors. And the other one is the development of thin film metallic glasses as magnetostrictive sensors. So these are the two different approach for developing such sensors. One such typical sensing I am showing you here, which is the magnetostrictive delay line sensing. So what happens is that there is one area where you have applied the magnetostrictive material, you have applied this bias magnetic field which is generating mechanical wave, and that mechanical wave is traveling. Then at another point you are actually picking up the signal, and then you are finding out that what is the delay in the arrival of this signal through the pipe, and in the instant the signal transfer from point A to point B due to the electromagnetic effect. Because the signal which is coming through the pipe, there will be a delay in that pipe, and that delay will be more and more if there are cracks inside the system, and that's why this delay can be a measure of the cracks, etc., or the defects in the pipe. This is another application of magnetostrictive system. It is called magnetostrictive mini actuator, or short form MMA. This has been developed by Professor Anjana Pandey's groups in University of Maryland. What you will see here is that there are these permanent magnets there on the two sides, and there is this Phenology rod in the middle, and as you are applying this electric field, and the permanent magnet already gives a bias to the system. So by applying the electric field on top of that, you can actually move to and fro this system, and the spring actually makes sure that you get more or less linear response for a good range of these. So that's how you develop this magnetostrictive mini actuators, which you can use for vibration control. There is another interesting way in which you can use it. It is called inchworm motors, like a Kisswaiter inchworm motor, and you can see here that initially there is no magnetic field, then you applied the magnetic field at this level, and then you do it here. So when you are applying it here, you are getting a deformation. Our task is, by applying it repetitively at different levels, we are actually shifting the position in such a manner that this displacement comes here itself, so that you are able to make some kind of an inchworm movement in the system by repeated application of magnetic field into a series of magnetostrictive materials. It is a very innovative concept. There is something like hybrid transducers also. In this case, for example, this is a steel disc, and this steel disc has clamps here, and there is a piezoelectric stack here. So, and also these are magnetostrictive rods. So that means if I apply magnetic field, they are actually going to give some kind of a force here, which will generate a torque and about the moment, about the center, and then that will keep the rotation of the disc. But if you want to control that rotation, then you use the piezoelectric stack, which will work like a clamp, and it will time to time it can actually stop the disc or slow down the disc. So thus, with the help of these two, you can generate various uniform motions in the steel disc system. Similarly, you can have hybrid sensors like partly piezoelectric and partly magnetostrictive, or you have amorphous ribbon, which is magnetostrictive, and then you have pickup coils, and also you have the PZTs. So the idea in this type of systems is that magnetostrictive sensor can be used in one part of the strain generation, whereas in the other part you can use piezoelectricity. Thus you can use magnetostrictive material for a larger range. So this is where we will close these discussions on magnetostrictive material. The references that you can use are Anjanappa's papers on magnetostrictive particulate composites, Dapino's paper on magnetostrictive sensors, and also the Carman and McKnight's paper on oriented terphenol composites. In the next lecture, I will talk about active smart polymers. Thank you.